Buckling of columns is basically buckling basically means bending, right? But the way it bends, it is completely different. So there is very subtle difference between bending and buckling. So we'll try to understand this and we'll try to know how to find the buckling load of any column. Any structural member that is subjected to axial compressive load is called as a strut, right? So we have seen frames, we have analyzed frames in our first year in engineering mechanics. So any member in this frame or any structure or any building, if it is having axial load and the load nature is compressive, then we can call that member as a strut. And if this strut is, it can be horizontal, it can be vertical, or it can be inclined. Now, if it is vertical, then the strut is called as a column, right? So strut is a general um name used for any member which is subjected to compressive load, axial compressive load. And column, whenever you say column, it means it is a vertical structure. These are very important in buildings, in any building or any structure, because they take the complete load of the structure. Now, how these columns fail? So let us see this first. So there are two types of failure that can happen in case of columns. First is the direct compressive stress. So if the columns are short, they get crushed and fail due to compressive load, right? So if the column is sufficiently long, then the load, crushing load that is applied, it produces two effects. One is the crushing stress, which is produced because of the load, and the second effect that is seen is the buckling of the column or bending of the column, right? So the long column fails because of combination of both of these. The load at which the column starts to buckle or bend is known as buckling load or critical load or crippling load. There are different names used for this. The load, that is the buckling load or the critical load or the crippling load, is less than the crushing load of the column. This is very important because even before the column gets crushed, it will start bending and then it will fail, right? So the load that you obtain from this is much less than the crushing load. Now we'll be seeing the Euler's column theory, and what are the assumptions made in this. First, let us have a look of this. The column is initially straight and load applied is truly axial. The cross section is uniform throughout the length of column. The material of column is perfectly elastic, homogeneous, isotropic, and obeys Hooke's law. Perfectly elastic and obeys Hooke's law, both are same, but somehow they had it was given in the book like this. Homogeneous means the composition is same at all the places in the column, and isotropic means it has same mechanical properties in all directions. The length of column is very large as compared to its cross-sectional dimensions. So the L by D ratio. D doesn't mean diameter, it is a dimension of the cross section, right? It can be depth, it can be width, whatever it is. So this ratio is sufficiently large. The shortening of the column due to compression is very small and is neglected. So when the crushing load is applied, when the specimen is being compressed, column is getting compressed, or compressive load is applied, there is change in length due to this compressive load. And what we are saying is this change in length or shortening of the column is very small and it is neglected. Failure of the column occurs due to buckling alone, right? The column bends and then it fails. That is the only failure that is considered. Now, the sign convention that is usually used is this. Now, this dotted line, blue color dotted line that you can see is the initial or the original position of the column, and upon application of the load the column has bent either this way or this way, or there is another case where it is bending like this. So if the column is bending like this, right, then this type of buckling is called as positive, and if it is bending into a concave shape like this, then it is called as negative, right? It has not no much significance in our calculations in future, but this is a sign convention which we need to remember. Now we will see Euler's equation for finding the buckling load or crippling load. The crippling load for column with any type of end connection, we'll see what is end connection later, is given by PE is equal to pi square EI by LE square, where PE is the crippling load and LE is the equivalent length of the column depending on the end connection. Now, depending on the end connection, how the column bends, we actually find the LE according to that. In the next slide we'll see this. Yes, so these are the four end connections which are commonly used in case of finding the buckling load. The first one is I have a column of length L and both the ends are hinged, right? When you have both the ends hinged, then when the crushing load is applied, the column bends like this into a concave shape, right? So the effective length in this case is the full length of the column. That is why we have effective length is equal to L. Now, in case of one end is fixed and the other end is free, that is what is shown here. So you can see when the load is applied, crippling load is applied or crushing load is applied, the column is bending like this. So in order to bring back this end of the column back to its mean position, that is like this, right, this line. So if you extend this, then this will go like this and it will come like this, right? So it is basically somewhat like this one. So the effective length will be twice of the actual length of column. So that is why we have taken LE is equal to 2L. When both the ends are fixed, so it is shown here, both the ends are fixed and you are applying the crushing load. So effectively, only half of this length is getting buckled, right? So here it is more or less straight, here also it is straight, and only this center half of the length of this column is getting bent. That is why we are taking LE as L by 2, and the last one is one end is fixed. You can see here this is fixed and the other end is hinged. So in this case the effective length is taken as L by root 2. So you have to remember these two things. PE is equal to pi square EI by LE square, and LE is equal to L when both ends are hinged, LE equals to 2L when one end is fixed and the other is free. LE is equal to L by 2 when both ends are fixed. LE is equal to L by root 2 when one end is fixed and the other end is hinged. Okay, let us go ahead. Now, this Euler equation, one of the assumption that we have made here is the length of the column is very large as compared to its cross-sectional dimensions. So it is seen that when you apply Euler equation to a short column, right? Euler equation gives correct result only for very long columns. Rankine, based on his experiments, arrived at following formula. 1 by P is equal to 1 by PC plus 1 by PE. What are these? P is the Rankine's crippling load. Okay. PC is the crushing load, which is sigma C into A. Sigma C is the ultimate crushing stress of the material, and A is the cross-sectional area of the column. And PE is the Euler's crippling load, which we determined earlier. Now let us analyze this. For short columns, that is length is less, right? The value of PE will be very high because it is divided by LE square. So if L is less, that is short columns, then LE is also less, and square of that when you divide it, right? The denominator is small, because of which the quantity PE will be very high, and PE in Rankine's formula is in the denominator. It is 1 by PE. So because of this, the ratio 1 by PE will be negligible, right? So what happens for the short columns? The Rankine's crippling load P tends to PC. PC is the crushing load, that is sigma into A. So basically what Rankine's formula gives for short column is the result will be very much close to direct compressive load. Whereas for long columns, the value of P will be very small because the length is large, right? In the equation for PE, we are dividing by LE square. So this quantity will be small. 1 by PE will be higher as compared to for the short columns. So then 1 by P is considerably large. Then the Rankine's crippling load P tends to PE, right? So basically, the Rankine's formula, it gives the appropriate result in both the cases, for short columns and for long columns. Whereas Euler's crippling load is, it gives considerably good result only for long columns. For short columns, it will not. Now we are just simplifying this equation. So 1 by P is equal to 1 by PC plus 1 by PE. So just cross multiply and take common denominator. And now I am substituting, what I have done is I have taken PE common from the denominator. So PE comes out and I get PE into 1 plus PC by PE. So this PE and this PE gets cancelled. Now PC is sigma C into A, and PE 1 by PE, right? So that is why I put this in reverse, LE square by pi square EI. Now I is the moment of inertia, is also given as AK square, where K stands for the least radius of gyration, right? So we are just rearranging the terms here. Then I get LE square by A K square. Now A gets, A LE square by A K square. This A gets cancelled, so I get the Rankine load as PC, that is crushing load sigma C into A divided by 1 plus sigma C by pi square E into LE square by LE by K whole square. Now this term sigma C by pi square E is called as Rankine constant, right? Rankine's constant A. So the Rankine equation becomes P is equal to Pc by 1 plus A into Le by K whole square, right? This ratio Le by K is called as slenderness ratio. Slender means under application of load, the column bends easily, right? So this property is called as slender, uh, right? So slenderness ratio basically it gives us an indication of how easily the column can be buckled. K is the least radius of gyration. Radius of gyration is determined by root of I by K. So we will see all this when we go to numerics. Any questions in this?